Hello everyone, this is Dr. Priya Hassan and welcome to the second week of our course, Astronomy with Archival Data. Today I'll be talking about the essentials of astronomy and essentially we'll first talk about parallax, which is related to the concept of distance in stars and astronomy. We'll also talk about the magnitude scale and some basics of photometry and spectroscopy. So typically when you look at stars, you know, the star gives you a very minuscule amount of light. And it is that very minuscule amount of light that we have to work with. But what is it that we actually observe when we actually look at stars? Now look over here, we have a short video. Is if you were looking at the same part of the sky through the night, right? This is an ESA video. And you can see over here, this is what the same part of sky would look like if you were looking at the same time of the night every day. Every day. And that's when you're actually getting a circle. I wonder if any of you could guess, how do you actually get this circular structure? How long would it take for you to get a circle for a whole star when you look at its movement in the sky? I'm going to repeat this again so that you can see it nicely. And here you can see the movement of this thing. And you can see the star is moving around in circles. And I'll give you the answer. So this typically takes place in a whole year. Okay, so in a year you can see that the star can take circles. This star takes a very big circle. There are some which take smaller circles. If you look at different stars, keep your eyes on different stars, you can see that they are taking smaller circles which are varying in size. And those sizes are basically a function of the distance, right? So if you had a star very close to you, the star would obviously make a bigger circle. And if it was further away from you, it would take a smaller circle. So now let us look over here. In this picture, what you see, the circle is actually happening in the period of time of a year. Okay, so let's see, this is the Earth which is going around the sun, and you're looking at a particular star. So if you saw the star in January, for example, it would be, say, in this direction, and then as you see it through the year, you will actually see the direction has changed. So the star was originally over here, and as you're moving this way towards July, so you'll see the star in this direction, then in this direction, this direction, this direction. So the star has actually effectively changed its position in the form of a circle, right? So this is typically what is happening in a year. So this is what is called an annular parallax. What is the parallax? Parallax is the change in position of an object. This is something which we often deal with. For example, if you look at this tree over here, and if the observer is standing over here, he'll see the tree in front of this peak, while this observer will see the tree in front of this peak. So if I were to measure this angle between these two peaks, right, take half of the angle and I were to take baseline, I can actually measure the distance, right? So this is the concept which is used behind parallax. And this is something which we constantly use with our own eyes, where the baseline is the separation between both our eyes, right? So you would have often tried it out, if you can try it out, that if you close an eye and if you try to hold your finger, it kind of becomes difficult because you don't have your double vision in the sense of two eyes to make your angle, to estimate the distance. So if you were looking at an object, like now I'm doing it, it's easy for me because I'm holding my own finger. But if I were to be doing it with an unknown object, I would actually not be able to estimate its distance if I look with only one eye. When I do it with two, that's when I actually get this angle. And with the angle, I can estimate the distance, right? So what you basically need to do is, in this case, you need to measure this angle accurately so that you can measure the distance. Now, obviously, you know that if an object is very close to you, it's going to move quite a bit. But if it's far from you, it's going to move very slowly. And that's what typically happens with stars because they're so far away from us. So this movement, this parallax angle is something very, very small, right? So here I've got another image of it in terms of a star. I look from viewpoint A, I can see the star in front of the blue stars, supposing this blue region is some region of the sky. And if I see it in terms of, from this side, I see it in front of the red background, right? And therefore, I kind of shift the position. The position was this and this. So I actually have this shift in position and I can measure this angle, which is called the parallax angle, right? So typically what's done with the Earth is if you observe a star in Jan and then you observe it in July, you see the difference in the movement which you're getting and you use that to measure the angle. Now the baseline is known to us because we are separating these two observations between a year, and therefore this half of this thing is 1 astronomical unit, which is 150 million kilometers, and therefore I can actually use this to get the distance to the star if I can measure the parallax. So what happens is my distance will therefore be 1 upon parallax. If I were to say my distance in terms of astronomical unit. So an astronomical unit, like I told you, is the distance between the Earth and the Sun, which is 150 million kilometers. So I can, this thing, and if I define this angle to be exactly 1 arc second, then I call this parallax angle. Then I call this distance to be 1 parsec. So therefore 1 parsec is the distance of the star at which it subtends a parallax angle of 1 arc second in a year, right? With the year as a burst line. So this was the standard way of actually finding the distances to stars, which are relatively close by. So here I have another picture showing you parallax. So you can see the blocks which are closer to us, like the red blocks or the white blocks, are moving a lot, right? While the blocks which are further away from us, for example, if I look at this orange block, it's moving much lesser because it's further away from us. And therefore you can see that there's this oscillation, this movement which is happening of the position of these objects, right? So when I actually look at the parallax, what is it? Like I said, it's the apparent change in the position of nearby objects relative to the background. So you have a background of stars and you can see what is the difference in the position of the star relative to the background stars. And based on that, we define the distance in parsecs to be the distance at which you have a parallax angle of 1 arc seconds, right? So here your distance will come to you in astronomical units. Sorry, this distance will come in terms of parsecs, which is where you have 1 arc second at a baseline of 1 astronomical unit. Now, what about parallax measurements? What are the kind of parallax measurements that we actually do? So the closest star we know to us after the Sun, obviously, is Proxima Centauri, which is a member of the triple system of Alpha Centauri. So the closest one in that, but the parallax for this is 0.76 arc seconds, right? The next star which we have, which is actually corresponds to a distance of slightly more than 1 parsec. Okay, 1 upon 0.76. The next star which we have is Bernard star, which has a parallax angle of 0.54, which is approximately 2 parsecs. Now the errors that were there generally in the measurement of parallaxes, it's about a milliarc second, and therefore your accuracy in your measurements therefore gets affected. So you cannot use this for something very, very far away. Now the Hipparchus satellite, which was a satellite we'll talk about later also, which actually measured parallaxes to 100,000 stars, it did it to an accuracy of a milliarc second, right? And therefore you could actually get the distances to about 100,000 stars using Hipparchus parallaxes. Now the new thing which has happened is what is called Gaia. Gaia is a new satellite of ESA, which very accurately measures the parallaxes of stars. And this does it to an accuracy of a micro arc seconds. And therefore with this new satellite, we have now the freedom of studying our galaxy to very good precision because of the parallax values. And we'll be having some special sessions on Gaia also, because like I said, Gaia is one of the newest databases which has a lot of potential and very good use. And it's basically based on the concept of measuring parallaxes. The other important thing which we can measure from a star is its luminosity or its flux. So let us first define what is luminosity. Now you know that a star basically produces light. And the total amount of energy that the star emits per second is what we call luminosity. So for the Sun, for example, it's 3.8 into 10 power 26 watts. Or if I were to put it in CGS, it would be 3.8 into 10 power 33 ergs per second, right? These are units of power, the amount of energy in unit time. Now the other unit, now we do not actually measure the luminosity for the simple reason that what actually comes to us is the flux, right? The flux is what actually is what we receive, which is if you had a light detector and you have a star, then you measure the amount of light given out by the detector intercepted in this area. And this area, whatever comes within the certain area, is what is called the flux. So it is the luminosity, it is per unit area. Okay. Now, what is the luminosity of an object, right? Now, like I said, the luminosity is the total energy which the star emits per second. And what does it depend upon? First factor it depends on is the radius of the star. And the second factor is its surface temperature. Okay. Now the flux is the total energy produced per second by each square meter of the black body radiator. So let us assume that stars are black body radiators. So that means they obey Planck's law of radiation. And given Stephen Boltzmann's law, if you were to put it, you would get it that this flux would be actually equal to sigma T power 4, where sigma is Stephen Boltzmann's constant and T is the temperature in Kelvin, right? Now, if I want to do it in terms of complete area, the complete area of a star, if I assume it to be a sphere, which is reasonably good, then I can say that the area of the star is 4 pi r squared. And therefore, the luminosity becomes this flux times the area. So it becomes 4 pi r squared sigma T power 4. This is a very important formula for you to understand. In the sense, you could have an object which is cold. Okay, the temperature is small, but if the size is very large, then your luminosity could be very large. For example, this typically happens in a kind of stars which are called red giants. Okay, these have very large radii and the temperature is low. These are cold stars. But because the radius is so large, the star becomes very, very bright. Conversely, you could also have a star which is very hot in the sense that T is very large, but the radius is small. For example, these are dwarfs. You could have white dwarfs, for example, but the temperature is large, the star is hot. But because its radius is very small, it's a contracted star, and therefore the luminosity of the star is low. So we need to keep in mind that what we think in our common assumption, that if you have a very bright star, that means that the star is big or it's very hot. That's not true, because you see in this luminosity formula, you have R as well as T coming in, and therefore both of them contribute to the luminosity of a given star. Now the other concept which we have over here is that of flux. What is flux? Flux is the amount of luminosity that comes to you per unit area, right? And therefore it varies with 1 by d squared. And therefore, if I were to compare two stars having flux A and B, if I were to do that, flux of A divided by flux of B would be the ratio of the luminosities, obviously, multiplied the inverse of the distances, right? So the flux of A will be luminosity of A divided by distance A squared, and this would be luminosity of B divided by distance B squared. And therefore, that's how we can compare the fluxes of two stars. So when we are typically looking at the brightness of the star, we also have to remember that what we are actually measuring or we are seeing is the flux. That is the amount of brightness that comes to us, right, in our detector, whatever we measure it. Now, this brightness, what was the way in which it could be measured? How would we measure the brightness? Now, the earliest records we have of people trying to measure brightness was done by Hipparchus. Now, look at Hipparchus. This is 190, 120 BC. Okay, and he's also considered the founder of trigonometry. And another very important thing which he discovered was the precession of the equinoxes. Now that should give you a very good idea as to how precise and how good Hipparchus was in his sense of measurement, right? To be actually accurately measuring the amount of the precession of the equinox, to find the position of the equinox, and then to actually measure the precession of it is something not very simple. Right? So what I have over here is what he basically did is he put stars in their order of brightness. So the brightest stars, he kept them as magnitude 1. The next brightest was magnitude 2, 3, 4, 5, 6. Right? So he actually put the scale, magnitude scale. Now this is called the apparent magnitude scale because this is the scales which we actually observe. If you were to see that these were the kind of objects you see, and your naked eye, the eye can give you the capability of looking at an object which has a magnitude of about 6. Bernard's star, the star we just spoke about, the second closest after Proxima Centauri, has a magnitude of about 9.5. Binoculars would give you approximately 10. A 1 meter telescope would give you a 19th magnitude. And accordingly, as you go to fainter and fainter, you will go to this. So what you can actually clearly see in this is that the magnitude scale is a reverse scale, right? Hipparchus actually put them in the sense of importance, right? So stars which had magnitude 1 were level 1 importance, right? And that the lower levels went to the fainter stars. So now we still stick to that convention in which if your magnitude is larger, that basically implies that the star is fainter, while a negative magnitude implies a very bright star. So for example, the sun has a magnitude of minus 26.8. which implies it's a really bright object, right? The full moon is minus 12.5. We also need to note that this is a logarithmic scale. We'll come to it in a minute. So the job of actually putting the scale in terms of numbers was done by Pogson, right? Pogson was actually from Oxford, and he was actually kept as the astronomer in India. He actually worked in Chennai, in the Chennai Observatory, which you see over here. And it's an interesting piece of information that he's actually been buried also in Chennai. You could actually find his grave is over there in Chennai. He worked there till he died. And what Pogson found is that this magnitude scale, which was there of Hipparchus, is essentially a logarithmic magnitude scale. In the sense, he noticed that there's a factor of 2.512 between stars of different magnitudes. So for example, if the magnitude difference between two stars is 0, the ratio of their fluxes is 1. If it is a difference of 1 magnitude, the ratio is 2.512. A ratio of 2 is 6.3. So essentially what he found, what was there is that a magnitude difference of 5 implied a brightness difference of 10, a factor of 10. So the flux varies by a factor of 10. And using this, he actually put the logarithmic scale for magnitudes. Logarithmic scales are very interesting because they actually apply to a lot of natural phenomena other than this, the behavior of an eye and other quantities, for example. So we need to know two things, that the magnitude scale is a logarithmic scale, number one, and number two, that smaller magnitudes are actually brighter, right? So if a negative magnitude, like I said, the magnitude for the sun, we come to this picture, you can see minus 26.8 is a very bright object, while an object which has a magnitude of 20 is a faint object, which can only be observed with a 1-meter telescope or even larger. So now here I have the formal formula in terms of magnitudes. Like I told you, 5 magnitudes gives you a difference of 100. So if you take the fifth root of 100, you get a factor of 2.512, right? So this actually tells you the difference between different magnitude scales. And therefore, if I had two stars which had magnitudes MA and MB, and I were to take the ratio of their fluxes, it would be, ratio of the fluxes would be 2.512 to the power of MB minus MA. So like I told you, if it is 0, you would have it 1. If you have accordingly, you will, if it is 1, you'll have 2.512. And accordingly, you can put the formula, which we'll see over here, which is MB minus MA is 2.512 log times this ratio, right? So here I have another scale again, which is showing you the magnitude scale, where you can see the sun being very bright over here. The moon kind of comes over here, and faintest objects are in this thing. So like I repeat, you have the logarithmic scale and it's a negative scale. The other concept, which is also very important, is the concept of absolute magnitudes. Now, we very well know that apparent magnitude is what appears to us, but that is related to the distance of the object, right? And because of that, even a fainter object at a close distance will appear to be very bright compared to a bright object at a larger distance. And therefore, if I want to compare, over here I have two stars. If I want to compare this star and this star in terms of its brightness, what I need to do is get them all to the same distance. If I can get them all to the same distance, then I can compare their brightness. Now that key distance was fixed to be 10 parsecs. So if stars are at a distance of 10 parsecs and I bring them all right over there, I can compare their brightness. And that's what I call the absolute magnitude. So the absolute magnitude of a star is the brightness of the star if it were at a distance of 10 parsecs. And this is a very useful scale. If I want to basically compare the brightness of different stars, I have to bring them to the same distance and compare them in that way, right? So I need to have, I can convert it to the absolute magnitude, right? So here I put this, and now what you have is, now replace the earlier formula what we put. If supposing if I have MA minus MB, but now in this case it's the same star, the small m refers to the brightness of the star, which is the apparent magnitude, while the big M is the brightness of the star, which is the absolute magnitude. So the difference between these two comes from this formula, which is minus 5 times plus 5 times log of D. So for example, if my D is 10, then this becomes 1 and becomes 5. So minus 5 plus 5 becomes 0. And therefore, small m is equal to capital M. So if the distance is 10 parsecs, then both the star, the absolute magnitude is equal to the apparent magnitude, right? So what you can see over here is that the apparent magnitude is less than the absolute magnitude if the distance is less than 10 parsecs, while it is larger if it is greater. So this difference, m minus m, is what we call the distance modulus, which is nothing but a function of the distance. So if I know the distance to a star, I can always convert its apparent magnitude to an absolute magnitude because I know the distance, right? And therefore, this is called the distance modulus, and it's a very important parameter in actually getting the absolute magnitude of a star, which then I can relate to the luminosity of a star. Now here is just an interesting example to show you what is the difference in the absolute and the apparent world. I'm sure most of you all know how to recognize this star called Sirius, and this is in a constellation called the Canis Major, which is a dog. This is supposed to look like a dog. This is the head of the dog. These are the front legs, the back legs, and the tail. And Sirius is the brightest star in the sky after the sun. But if I were to use all these stars and convert them to absolute magnitudes, this is apparent magnitudes, what appears to us from the Earth. If I were to convert it to apparent magnitudes, this is what Canis Major would look like. And our poor little Sirius, which you can see over here, as the next brightest star after the sun, appears a pretty faint star, right? So what we have to do is, our eyes are fooling us, obviously, because of the variation in distances. When we study them, we have to use our knowledge of the distances to stars to convert their brightnesses. And now this is what Canis Major would look to you like. And actually, to me, since I'm so used to thinking of Canis Major as a dog, I still think of it as a dog because it's a nice head it has. You have the front foot, you have the back foot, you have the tail. So I think Canis Major still can be called Canis Major on an absolute scale. However, Sirius will not be the next brightest star after the sun in our skies. Now, magnitudes in this way can be measured, but you know that this flux varies in wavelength, right? Even if the star is a black body emitter, it's going to emit differently in different wavelengths. And therefore, it varies with wavelength. And in principle, you would have to measure the brightness of a star in different wavelengths to actually get its total amount of brightness, right? So ideally speaking, you would have to integrate all its brightness coming in different wavelengths. And therefore, one of the things what we do is what is called multi-wavelength astronomy, where we actually measure the brightness of an object in various wavelengths, and we use that to extrapolate or interpolate and get what we call the bolometric magnitude. By that we mean the total amount of brightness coming from a star in all wavelengths. We want to get it in all wavelengths. So that's what we call bolometric magnitudes. Now, what is photometry? Photometry is nothing but measuring photons. We know that these objects are basically giving us photons, and we want to measure these photons. Now, I'm not going to go into details about telescopes, and therefore I request you to go through the lecture which is there on telescopes, which is there on my website, on my YouTube page on telescopes. You can have a look at it. The link has been also provided. And you can go through that. But let us see what are the magnitude limits which we have for detectors. For the human eye, the pupil size, say let's take it 2 millimeters, it could vary from 2 to 5 millimeters. It gives you a 6th magnitude. That's the faintest you can see, and that too when the sky is very dark and very good, right? If you go for a 6-inch kind of a telescope, you typically go to about 12.9, 13 magnitude is what you'd see with a 6-inch telescope. With an 18-inch telescope, you'll go up to about 15th magnitude. And there's a simple formula which actually gives you the conversion. So in general, what you can see is that for the telescope, the magnitude, limiting magnitude that you will go out to would be approximately 2 plus 5 times log of D, where this is the D value in millimeters. So once again, if I look at my 6-inch, the 6-inch is about 152 millimeters, which gives me log as 2.18. And therefore, this would be 2 plus 5 into 2, approximately 12 plus. So this is 12.9. Similarly, my 18th magnitude is 457 millimeters, which is 2.65 in terms of logs. So it would be 2 plus 5 into 2.65, which gives me approximately 15.3, right? So that's the immediate way in which how you can find out what would be the brightness limit you are going to go to, depending upon the telescope you're going to take, a 10 meter or a 20 meter, etc. Right? Now, what are photometric systems? Now, to measure the brightness of a star, like I mentioned earlier in the first lecture, we spoke about what are called filters. We use filters, that is, the filter will only permit light of a certain wavelength to come to the telescope, right? And there are three kinds of filter systems which are used. One is what is called wideband systems. For example, the UBV system, which we'll talk about in a minute. And in this, the filter width is about 9,000 angstroms. You could also have intermediate band filters. Basically, this is just telling you the width, right? What is the width of it? Of about 200 angstroms. And narrow band is basically marked at a certain spectral line. For example, you want to look at the H alpha line. So then you could have an H alpha filter, which typically looks for emission coming in the H alpha wavelength with a plus minus of 30 angstroms. So that you can see within that this thing. So if we look at the UBV system, right? UBV system is basically made up of three filters. One is the U, which is the ultraviolet. You can see that the central wavelength for the U filter is at 3,600 angstroms. The B filter is what you have 4,400 angstroms. The V part of the filter is 5,500 angstroms. This has a width of about 1,000 angstroms. Okay, so that what's going to happen is that you are going to center it around this, and you're going to take plus minus 500 and accordingly take the amount of light that comes within the filter. Now, why do we basically do this? Why do we put filters in the photometry, the photons we measure? There's a very key reason why we do that, and that's this. If we assume that a star is a black body radiator, right? This is a curve for black body radiation, which I have over here. If I actually use filters, that means I'm getting points on this curve. So for example, if I do it in visible light, say I measured in the ultraviolet, and then I did it in the blue, and then I did it in the yellow. So typically what do I get? I get 3 points on this black body curve, right? So for example, if I look at the sun's emission, the sun actually emits something which is this black curve, okay? It looks like this. But if I were to approximate it to be a black body emitter, it would give me this kind of a curve, which is slightly smoothened over here. And what is the advantage? If I have UBV reading of the sun, I observe the sun in these three filters, I will have 3 points on this curve. And once I have 3 points on this curve, right, I can actually fit it to a black body curve, and I can get the temperature. So that's exactly what we do for the sun. So for the sun, if you measure its brightness in 3 different filters, you'll get 3 different points on this black body curve, right? I fit it to this black body curve, which corresponds to 5,800. So this is the temperature of the photosphere of the star, of the sun. And therefore what happens is, if we use filters and we measure the brightness, what we are basically doing is we are sampling. We are making measurements of the brightness of the star at different wavelengths, right? So we are sampling the black body curve of the star at different wavelengths. Now, this is what we basically call color. So for example, if I measure a star in the B band and I measure the star in the V band, which is equivalent to my giving the apparent magnitude in the B band and the apparent magnitude in the V band, right? Then I can just say my B minus V is equal to MB minus MV, which is the ratio of this. And I know that this is going to be a function of the temperature. And therefore, if I know the color of a star, by the color I talk about, it is the difference in the brightness in 2 filters, in 2 different filters, then I can actually estimate the temperature of stars. And therefore, here I've shown you a plot of B minus V versus temperature. These are only for stars which are called the main sequence stars, right? Again, I direct you to look at those videos which are there. There is a video on stars, and you can see some basics on stars, and you'll see what are main sequence stars. So you can see main sequence stars are adult stars. Most of the time of stars is spent in the main sequence phase. The sun itself is a main sequence star. And you can actually see that the color, the B minus V color, is proportional to its temperature. So therefore, if there's any given star for which I can measure its B minus V, I can actually get the temperature of the star. Right. The other small part which I'll be talking about is spectroscopy. The other very important and most effective way of studying an astronomical object is through spectroscopy. What do we mean by spectroscopy? You have a source of light. Yeah, I have a spectroscope. For example, here I have a prism. What does the prism do? It disperses the white light into its constituent colors. And that is what is called a continuous spectrum, where I'm getting light in all wavelengths. Now, supposing if I have a heated gas, right, then this heated gas is going to give me some amount of emission lines, and I will get some brighter lines which are brighter than the continuous spectrum, which you can see here, which are called our emission lines. If there's a cold gas, then what does the cold gas do is that I have the source of light over here. This cold gas is going to absorb certain amount of radiation which corresponds to jumps in their atomic spectra, and you will get what are called absorption lines. Now this is a very, very important piece of information. It's like a fingerprint, because every element has characteristic wavelengths which it will emit or absorb. So once you can define what is the lambda or what is the wavelength at which you have this absorption or emission taking place, you can immediately state which is the chemical composition of this element, as well as some more features depending on the intensity of lines, etc. You can use spectroscopy to actually study the chemical composition of a star, right? And even study the temperature through other understanding, which I'll talk about in a minute. So first thing is, again, how do you find the temperature? Like we said, you use the blackbody radiator concept, which we already did. Like I said, when you get the spectrum, the continuum spectrum is going to be coming to you because of brightness. So you have this continuum spectrum. Using that, you can get the brightness. Like I said, you could also have absorption lines as well as emission lines, depending upon the gas which is there between the source and you, right? So if you have typical stars, you will actually see the spectra of stars. If we take the spectra of stars, you'll see certain lines over here. You can see here, these ones are all absorption lines, which you can see over here. There are some emission lines also coming over here. And over here, there are different stars, okay? So we talk about that at a later class. There are different spectral types of stars, depending upon how hot the star is, right? So O-type stars are very hot stars, while as you're coming down to M-type stars, these are much cooler stars. And therefore, you can see that the spectrum is much more abundant, right? There are much more spectral lines. And because these are much cooler ones, and these are actually used to identify chemicals, which you can see are marked on these spectra. It actually tells you which are the chemicals sitting in these stars which are causing these important lines. Now, when we look at spectroscopic data, these are just guidelines, what you need to see when we are using spectroscopic data. You need to check the resolution of the instrument that you are using. Now, what is spectral resolution? It is lambda by d lambda, okay? So, for example, if you have a separation, the sodium lines, which you do in the lab often, your d lambda is the separation of the sodium lines, while lambda is the average value. So it's basically telling you whether you can resolve those two lines or no, right? So the resolution will basically, so for example, when we do spectroscopy, if you're using a bandwidth of 1000 angstroms, you're doing very low resolution spectroscopy. In a way is what you do with narrow bands, when you're taking a narrow band. So photometry in a way is low resolution spectroscopy because you're getting points at some lambdas, right? While if you use a spectrometer, you can get medium high resolution spectroscopy, which can range from 100 to 10,000 value of resolution. And obviously that will make a difference on your resolving power. How well can you resolve your thing, right? So you want your d lambda to be as small as possible so that you can see a smaller variation in lambda, due to which you want your R to be large, right? So depending upon which instrument you're taking spectroscopic data about, you need to check what is the resolution value for that instrument to actually see whether what kind of spectra are you talking about. The other important thing one thing which can be done with spectra is also identification of spectral lines. So we can also download spectra of various stars, and you can use that to identify the spectral lines on that spectrum. So if I, for example, were to give you this spectrum, which is a O-type star, and give you hydrogen spectrum, you can use that to actually identify the different hydrogen lines which you have over here. So here's an H alpha line. This is the H beta, the H gamma, H delta, various hydrogen lines. So you can actually identify the spectral lines. You can actually also study what is called the equivalent width. By equivalent width, we mean what is the width of the spectral line which you're going to get. You're actually going to see how does this, if I get this whole area which is there inside this curve, I find a rectangle which also has the same amount of area, and that is what is called the equivalent width. Now, the equivalent width of spectral lines can vary depending upon the temperature of the star, the pressure available over here. You can also have a shift in the spectral line, which is called the Doppler shift. And this is basically what is used to measure the velocity of objects, right? So your Doppler shifts could be useful if you're studying exoplanets to actually look at the shifts in velocities. They can be useful if you're studying quasars to actually get the redshifts of quasars. They are useful in studying the expansion of the universe if you want to get the Hubble expansion of the universe. So Doppler shifts are very important. So you scale spectral lines and find the shift in the spectral line, as well as the broadening of the line can give you physical conditions of the star, as well as identification of lines gives you the chemical composition of stars. And therefore, spectroscopy is a very effective method of doing it. The only problem for spectroscopy is that supposing you have an object, which is a faint object, and you want to do spectroscopy, by that you mean you're going to take light only in a particular wavelength. That light becomes very, very small, right? It's very difficult. And therefore, big telescopes are typically what are used for spectroscopy. While the poor man's instrument is basically the photometry approach, because in photometry, what happens is, since you have larger widths, right? You have larger widths of your filters, you can catch photons much more easily. And therefore, a smaller telescope can let you look at more fainter objects compared to spectroscopy of the same object with the same telescope. So if you want an object to do spectroscopy, you need your telescope to be far better than if the one which you would require for photometry. Right. So I'm going to wind up with this, and I hope things are clear to you. And I'll be putting up the second quiz on the website. And so please do the quiz, and let's hope that you can see that you understood some of the concepts over here. Thanks a lot. Bye-bye.